Hi and welcome everyone, my name is Lon. This tutorial will focus on encapsulation in C#. Before we get into it, please subscribe, it's free and can help you reach the next level in programming and technology. If you're already subscribed, please hit the bell icon to be notified of future, valuable content which will be coming soon. Right, object-oriented programming is a paradigm in computer programming. C# is an object-oriented programming language. Classes can serve as prototypes or templates for objects, where, for example, members of classes like properties and fields can be used to store and change the state of an object. Methods, for example, can be used to invoke object behaviors and in doing so change the state of the object. So a very simplistic example would be a car can be represented in code as a C# class. This class can contain a method named startEngine. The developer can create a new car object using the new keyword and call the startEngine method. Calling this method invokes many procedures that need to be run in order for a car engine to start, which then results in the car object state changing to engine started. So you could have a Boolean field or property member of this object that can be used to store the state for the object. Let's call this field or property engine started. If the startEngine method has been called, the engine started field or property could be set to true in order to store the appropriate state of the object. The main object-oriented principles are encapsulation, polymorphism, and inheritance. The principle of abstraction can also be included. We are going to focus on just one of these principles in this tutorial, namely encapsulation. What is encapsulation? Encapsulation is the practice of encapsulating data and functions into a single unit, a class for example. The need for encapsulation is to protect or prevent the code data from accidental corruption. This protection can be implemented through the use of access modifiers. The available access modifiers in C# are applied to types or members through the following keywords and keyword combinations. Public. If a type or member is public, it means the type or member can be accessed by any other code in the same assembly as where the type or member is declared, or by code in another assembly that references it. Private. If a type or member is private, the type or member can be accessed by code resident in the same class, but the member or type cannot be accessed by code external to the class in which the member or type is declared. Internal. If a type or member is internal, the type or member can be accessed by any code within the same assembly but cannot be accessed by code within another assembly. Protected. If a type or member is protected, the type or member can only be accessed by code within the class in which the member or type is declared, or by a class derived from the class in which the type or member is declared. Protected internal. If a type or member is protected internal, the type or member can be accessed by any code in the assembly in which it is declared, or from within a derived class in another assembly. Private protected. If a type or member is private protected, the type or member can be accessed only from within the assembly in which the type or member is declared, by code in the same class, or from within a type that is derived from the class in which the private protected member or type is declared. So the principle of abstraction is often confused with the principle of encapsulation. I would say the difference between the two concepts is that encapsulation is concerned with the protection against unintended access to data belonging to a class member or type. And I would say abstraction is a design principle used for abstracting an interface for an object in order to decouple design implementation from code logic implementation detail. So for example, a real-world function of starting the engine of a car. All a user needs to know in terms of starting an engine of a car is to turn the key in the ignition. So in code terms, you could have a car object that contains a method named turnIgnitionKey. Calling the turnIgnitionKey could set in motion many complex processes which are executed in sequence to start the car's engine, but all that needs to be exposed is the turnIgnitionKey abstraction. The complexity involved in starting the engine is abstracted. Knowing the detail of how the turn ignition key method works is not necessary to start the engine of the car. Calling the turn ignition key method is all that is required to start the engine of the car. An even more simple example is switching a light on and off. You don't need to know about circuits, electrons, voltage, amps, resistance to turn on a light. You only need to know how to operate the light switch. In C#, abstract classes and interfaces can be used to implement this design principle. I won't go into too much detail regarding the principles of inheritance and polymorphism, because these principles will be explored individually in detail in upcoming tutorials. Very basically, the principle of inheritance allows for a class to be based on another class. The class based on another class is known as a derived class. The class on which the other class is based can be referred to as the base class. In C#, an abstract class is a class that cannot be instantiated directly. The principle of polymorphism is the provision of a single interface to entities of different types. The word polymorphism has Greek roots, poly meaning many, and morph meaning form. A polymorphic object can take on many forms, but this principle will be explained in detail in an upcoming tutorial. So let's explore the principle of encapsulation through a code example. We are going to create a mock application, if you like, to highlight the use of encapsulation in C#. The idea behind this application is to enable the use of a handheld remote device to control office facilities for one or more offices. We are going to mock functionality that remotely logs into one or more offices. If authenticated, the user is able to toggle the lights on and off, as well as arming and disarming the security systems for the appropriate offices. So architecturally, this is how a system like this might look. And this is a very simplistic overview. A device with an internet connection connects to a web service, perhaps hosted in the cloud, like for example, a web API hosted by Microsoft Azure. The device calls an appropriate web service method to log into an office. If authenticated, the device will be able to switch the lights on and off for the relevant office. The device will also be able to call relevant web methods to arm and disarm the security system for a particular office. Once again, note that this is not a real-world, fully developed application, but simply demonstrates a concept and focuses on the object-oriented principle of encapsulation. So as you can see, I've created a solution named Office Building Automation. This currently contains one project based on the .NET Core console application project template. I've included a link in the description below which points to a location of a tutorial that demonstrates creating a .NET Core console application project. So once the project generation process is completed, a solution that can contain one or more projects is created. You can see this by viewing the Solution Explorer window. Each project in a solution will be compiled into its own .NET assembly. I've included a link in the description below for more information regarding .NET Assemblies. So to add a new project, right-click the Solution node at the top of the Solution Explorer window. Then click on the Add New Project context menu item. You will then see a dialog box, and in its title bar, you should see the Add New Project text. So in the name field, let's type Office Building Automation API, and then click the OK button. And you can see in the Solution Explorer, our new project has been created, Office Building Automation API. This process has also generated a default class named Class 1. Let's right-click the node for the class named Class 1 and click the Delete Context menu item. Then let's add a new class. So we right-click the Office Building Automation API project node and then click the Add New Item context menu item. We can then see a dialog box with Add New Item text followed by the project name text, Office Building Automation API in the title bar. We want to add a class, and we can see the class item at the top of the right window pane. In the left window pane, you can see that it is a member of Visual C#. And let's give our class a name. Let's name the class Office Building Fake Web Service. This tutorial is focused on the concept of encapsulation, so we are not going to include much code implementation in this class. I'm attempting to create a solution that resembles a real-world solution, but obviously it would be impractical to create a real-world solution for this tutorial, so this is a mock web service if you like. Let's say that it is the client-side interface for the calling of a RESTful web service API. We are not going to go into the details of web services or REST architecture in this tutorial, but these are very important concepts I would encourage you to explore. I do intend creating courses on these technologies in the future. REST stands for Representational State Transfer. For this tutorial, this class represents a client-side interface for communicating with server-side code. So to save time, let's fast forward the creation of the code for this class. As always, all code created in this tutorial can be downloaded from GitHub. If you download the code, you can obviously look at the code in more detail at your own pace. Please see the details of where you can download the code below in the description. Note that the access modifier used in this class and all method definitions use the internal access modifier. This means that this class and its methods can only be accessed from within the assembly in which they reside. So to be clear, the first project that was created by default when the solution was first created will not be able to access the Office Building Fake Web Service class or any of the methods contained within this class, because this class resides in a different assembly. Remember, each project within the solution will be compiled into an individual .NET assembly. If a class's definition contains the internal access modifier, only code within the assembly in which the class resides will be able to access the class. All other assemblies will not be able to access the class. The same principle applies regarding internal methods, fields, properties, etc. So very briefly, the methods here are login. This mock method, if you like, is for the authentication of a user to be given permission to manipulate an office's relevant facilities, in this example the lights and security system, remotely. A unique security token is returned by this method if a user is authenticated. If the token value of 0 is returned, the user cannot control the facilities of the relevant office. The next method is the isLightOn method. This method returns the status of the lights within the relevant office. If the lights are currently switched on, a Boolean value of true is returned from this method. Conversely, if the status of the lights within the relevant office is switched off, false is returned. isSecuritySystem armed returns true if the security system is currently armed and false if the security system is currently disarmed. Switch light on sends a message to the server indicating that we want the lights in the relevant office to be switched on. Switch light off sends a message to the server indicating that we want the lights in the relevant office to be switched off. Arm security system sends a message to the server indicating that we want to arm the security system for the relevant office. Disarm security system sends a message to the server that we want to disarm the security system for the relevant office. Notice that a security token must be sent through to each of these methods. This is just to simulate the stateless nature of client-server communication across the internet. In the real world, there are many ways of facilitating this better, for example, embedding the security token within the headers of the HTTP messages. This tutorial is focused on the object-oriented principle of encapsulation and not on client-server communication across the internet. I thought it would be better to create a quasi-real-world context for this tutorial, rather than just discussing the relevant concepts in isolation. Okay, so the next class we wish to create is the Office class. Let's go through the same procedure we did to create the last class. And let's fast forward the code creation process for the Office class. Let's discuss the code within this class. First of all, the class is public. So the constructor in this class is used to instantiate our Office Building Fake Web Service class. We are able to access the Office Building Fake Web Service class because it has an internal access modifier and resides within the same assembly as the Office class. And you can see that the access is limited through the use of the private access modifier for the Office Building Fake Web Service object which is declared within the Office class. This means that the Office Building Fake Web Service object can only be accessed by code within the Office class. Whereas the internal modifier would limit access to an object instantiated from code within the same project, the private access modifier limits access to code created within the same class in which the Office Building Fake Web Service variable is declared. The security token must be accessed internally within the class, so access to this variable is limited to code within the class in which it is declared. This is why the private access modifier is used to define the security token variable in the Office class. The isLightOn Boolean variable is public, and so is the Boolean variable isSecurityArmed. The integer variable Office ID is also public. This means that read-write access to these fields is enabled from any code within this solution. I want to point out that it would in fact be better to encapsulate the isLightOn and isSecurityArmed variables within read-only properties. We could have made these variables private and the properties that protect these variables public, and also read-only. We can make a property read-only by only implementing code for the get part of the property and omitting code for the set part of the property. This course has not covered properties in great detail. Properties will be explored in upcoming tutorials. So this is a good example of implementing encapsulation. By doing this, we would be protecting the isLightOn, isSecurityArmed, and Office ID values from being changed inappropriately from code external to this class. I'm going to leave these as public. If you download the code, perhaps you can change these variables to have private access modifiers and wrap these variables in read-only public properties. I'll provide guidance in the code that can be downloaded from GitHub through comments. So the login method wraps the call to the web service login method. If the user is authenticated, the security token will be greater than 0. This code is deliberately simplistic, just for the example. So if the security token is greater than 0, we get the current status of the lighting and the security system. So when the toggle lights method is called and the status of the lights is that they are switched on, the appropriate web service method is called to relay a message to the server to turn the lights off. If the lights are off, when the toggle lights method is called, the appropriate web service method is called to relay a message to the server to turn the lights on. The same logic is applied for the toggle security system method. The only difference is that the code is specific to arming and disarming the security system. Note that the toggle lights and toggle security system methods are marked as internal methods. This is because we have decided that we do not want the code from outside the Office Building Automation API assembly to access these methods directly. We only want the code from within the Office Building Automation API to be able to access these methods. The main reason for this is that we want code external to the Office Building Automation API assembly to access functionality through the classes that represent handheld devices. For example, we are going to create a class called Remote Device Office Control. This class serves as an allegorical example for a remote control Internet of Things device that can be used to remotely control the lights and security systems for one or more relevant offices. We also want to develop a class later in the tutorial for an app that could run on a handheld device running, for example, iOS or Android operating systems. These classes are allegorical and not intended to function on these operating systems. We are only interested in demonstrating the concept of encapsulation in this tutorial. So let's first create a base class for our remote office control functionality. Let's create a class named Base Office Control. Let's first create a variable that will hold an array of Office objects. Notice the access modifier combination of protected internal has been used to constrain the access level for this variable. Protected internal means that this variable will be accessible to classes that inherit from the base office control class, and this will be true for classes within the assembly in which the class resides, as well as from offices external to this assembly that are derived from this base office control class. This variable will also be accessible to code that resides within the same assembly in which the variable is declared. This class will serve as a base class for other office control implementations, for example, a remote Internet of Things device or an iOS app. And you can see that the constructor accepts one parameter, which is an array of offices. The variable that will store the array of offices is named offices. It is constrained by the protection level imposed on the variable through the use of the protected internal access modifier. Let's fast forward the code creation for the rest of this class. You can see that we have created two virtual methods that can be overridden by derived classes. The functionality in these two methods loops through an array of offices and implements the appropriate toggle functionality for switching the lights on and off, or arming and disarming the security system for an array containing one or more offices. You can see that at the bottom of the class, a method to log a line of text to the console screen has been created. This method, named loginfo, has a protection level imposed on it through the use of the private protected access modifier keyword combination. This means that derived classes within the assembly that this class resides will be able to access this method. The method will also be accessible from code that exists within the same class in which the loginfo method resides. Classes that exist outside the assembly in which this class resides that derive from this class will be unable to access this method. All code that exists outside the class in which the loginfo method exists will not be able to access the loginfo method. But you can see there are red squiggly lines under the loginfo method. Now let's hover our mouse pointer over the red squiggly lines. The pop-up message clearly tells us the issue. Feature private protected is not available in C# version 7.0. Please use language version 7.2 or greater. So it is important to note that the private protected feature was introduced with version 7.2 of C#. The projects in this solution are currently set to version 7.0. So let's click Show Potential Fixes. Then let's click the Upgrade All C# projects to version 7.2 option. And the red squiggly lines disappear because our project implementing the private protected feature has now been successfully upgraded to language version 7.2. Okay, so let's create a class that will derive from our base office control class. Let's name this class Remote Device Office Control. So this class denotes a remote control Internet of Things device, which is like a TV remote control that allows the user to manipulate certain office facilities remotely through a series of toggle buttons. Obviously, this class serves as a metaphor and is not a real-world implementation. Note, methods for our class are public because we want to enable code outside the assembly in which these methods reside to be able to access these methods. And note how we are able to use the base keyword to access the loginfo method in the parent base office control class. The private protected access modifier does not prohibit access to the loginfo method from a derived class that exists within the same assembly as the base class where the private protected method resides. So we are using the base class's loginfo method for our logging functionality within the remote device office control derived class. And let's also create a test class, which will be the last class we create for our Office Building Automation API project. This test class serves as an allegorical testing facility where we can test the functionality of our office control interfaces. The idea is that we can pass our office control implementations, and this test class can output results letting the tester know if a particular implementation of the office control functionality is working as expected. And this is interesting. We are creating a private method named getTestOffices as string, which serializes relevant office IDs as a string and returns it to the calling method. Remember, in our office class, we created a field named offices to store an array of office objects and gave it the access modifier of protected internal. code within our test office control class would not be able to access the offices field if it had been declared with only the protected access modifier. This is because the test office control does not derive, i.e. does not inherit, from the base office control class. An object of type base office control is passed into the constructor of this class. The relevant methods of the base office control are then wrapped within the relevant methods of the test office control class. The protected access modifier would allow access to a derived class that could access this field using the base keyword. Note, the test office control is not an office control. It is designed for testing office controls and therefore does not inherit from the base office control class. But we still need to be able to access functionality that uses the offices array. So this is why we have used the combination of protected internal as the access modifier for this field. The internal keyword means that the offices field can be accessed from anywhere within the assembly in which the offices field is declared. The protected keyword ensures that the offices field can also be accessed from any class derived from the class in which the offices field is declared. Note that we are accessing the offices field from the remote device office control class, which derives from the base office control class. This would also be enabled if only the protected access modifier were used in the declaration of the offices field. The offices field is also accessible from the test office control class, which is not derived from the base office control class. The reason the offices field is accessible from the test office control class is due to the internal access modifier applied to this field. The test office control class is in the same assembly as the base office control class where the offices field resides, and the internal access modifier enables the offices field to be accessible by any code within the same assembly. A protected internal member of a base class is accessible from any code contained within the assembly in which the protected internal member is declared. It is also accessible to code within a derived class located in the same assembly or derived class that exists within another assembly. Right, let's implement code from the main method in the Office Building Automation assembly to consume code within the Office Building Automation API assembly. So first we need to reference the Office Building Automation API from the Office Building Automation project where our main method resides. You can see that when we try to create a using directive at the top of our code, we are able to see the Office Building Automation namespace, but this is not the namespace we require in our using directive. So we must create a reference to the Office Building Automation API assembly so that we can create a using directive with the Office Building Automation API namespace. So in our Solution Explorer window, under the Office Building Automation node, right-click on the Dependencies node. Click the Add Reference context menu item. The Reference Manager dialog box will appear. There is a tree view on the left window pane, and the item selected is Project's Solution. So you'll see there is a checkbox next to the project that we want to reference, marked Office Building Automation API. Let's click the checkbox so that a tick is displayed next to it, and then let's confirm our intention to reference the Office Building Automation API assembly by clicking the OK button. We can now include the appropriate namespace in our using directive at the top of our code. So the directive now reads using Office Building Automation API. Okay, I'm going to implement the calling code that will consume the Office Building Automation API to toggle the light switch for 3 offices and toggle the security system for the relevant 3 offices. In the interests of saving time, I'll go through this fairly quickly. Remember, you can go through the code at your own pace. All you need to do is download the code from GitHub. Details of where you can download this code are below in the description. Let's create 3 office objects. Let's log into all 3 of the offices. Obviously, this is not a real-world example regarding security. I've had to simplify certain aspects in order to keep the focus on the topic of this tutorial, C# encapsulation. So this is mock code, if you like, for logging into the offices where we wish to remotely control the lights and security of the relevant offices through toggle buttons on a handheld device. So let's store these Office objects in an array of the Office custom type. Let's create a reusable method for writing user instructions to the console screen. Let's create a remote device Office control object, which is analogous to an Internet of Things remote control device. Let's then create an infinite loop. We'll use a while loop for this. So this loop will continue to iterate indefinitely because the termination expression always returns true. This infinite loop will allow us to keep the code running until the user terminates the application by pressing the spacebar. So in the code, we are using the else if block to allow the user to toggle the light switch using the L key, toggle the security system using the S key, and terminate the application using the spacebar key. And if we press an incorrect key, text in a red font is outputted to the console screen, reminding us of how to use the application. So let's test the code. So let's toggle the lights. Let's turn the lights on. Let's turn the lights off. Let's arm the security system. Let's disarm the security system. What happens if we press an incorrect key? And the appropriate red text letting us know how we should use the application is presented to us. Let's toggle the lights and security a bit more for good measure. And let's press the spacebar to terminate the application. Great. So let's create another derived class of the base Office control, but this time within a different assembly to where the base Office control class resides. This implementation is a metaphor for an app on a handheld device being used to control certain facilities on the relevant offices. So let's fast forward the code creation process for this class. Okay, so we have red squiggly lines under the base.loginfo method. Why is this? If we hover our mouse pointers over the red squiggly lines, we see a message stating that this method is not accessible due to its protection level. What was its protection level? Private protected. A private protected member will not be accessible to a derived class that exists in a different assembly. A private protected member is only accessible to a derived class within the same assembly as where the private protected member is declared, and to code that exists within the same class as where the private protected member is declared. So what happens if we change the private protected method to just a protected method? Yes, this means we can now access the method from the derived class. But the private protected access modifier was implemented for a reason. Let's say the reason was we don't want classes that exist outside the Office Building Automation API assembly to use our inbuilt logging method. A derived class that exists outside this assembly must be forced to implement their own logging. Right, let's create an object from our new app implementation of the base Office Control base class and run the code. And we can now toggle the lights, toggle the security system, and when we are finished, end the application by pressing the spacebar. And we'll quickly demonstrate using the test Office control. So we can pass the app Office control object to the test Office control class's constructor. And run the code. And outputted to the screen is the test status of the appropriate Office control in a green font. You can see the 3 Office IDs above the green text. Now this highlights how we have used the protected internal modifier to allow access to the Office's field in the base Office control class. So let's see what happens if we change the protected internal access modifier to a protected access modifier. If we compile the code, we get an error. The error message states, base Office control.offices is inaccessible due to its protection level. So because we wish to access the Office's field from a class test Office control within the same assembly as the base Office control, and the test Office control merely wraps the functionality in the base Office control class, and does not derive from the base Office Control class, we need the access modifier to enhance access from the access provided by the protected access modifier to access provided by the protected internal modifier. So finally, let's run a test against the remote device Office Control object. And the results are as expected. Excellent. Please download the code from GitHub. Details of where you can download the code are provided in the description. By all means, play with the code, try to improve the code. This code serves as a guide for understanding C# encapsulation. Please give this tutorial a thumbs up if you feel you've gained value from viewing it. Please subscribe, it's free and can help you reach the next level in programming and technology. And please smash the bell icon to be notified of future valuable content, which will be coming soon. Please feel free to engage with me in the comments section. Thank you and take care.